let me go back to my magic square with slightly different form. I said there are four fundamental forces, the three forces, the electromagnetic force, the weak force, the strong force, and then there is gravity, the fourth force. But number four comes in another way too. We live in four-dimensional space-time. Most of the time we think we do anyway. Sometimes we go into higher space, but 4 dimensions is the real world of real physics. So the number 4 comes in twice. Once because there are 4 fields, 4 forces, once there are 4 dimensions. And I think I want you to think of that as one lot of 4 is going across the magic square and the other one is going down the magic square. So going across the magic square you see the different fields. Going down the magic square you see increases in dimension. And this is a rough sketch. And it's not quite as straightforward as that because there are links between all the different parts of the diagram. Roughly speaking, like this. So the top row you can think of as quantum mechanics. And here you would have, from the point of view of geometry, you would use, classical geometry, you would use representation theory of Lie groups. These are very much used in quantum mechanics. And then if you go to 2 dimensions, I mean, from this point of view, 2-dimensional quantum field theory is one space, one time. And the particular class of theories I want to call conformally invariant theories, which depend on the complex structure of Riemann surfaces. This is a very well developed branch of quantum field theory. Beyond quantum mechanics, so to speak, is time and no space. No space is finite dimension. But the first step in quantum field theory is to go from here to there. And the theory of Riemann surfaces plays a very important role, and beautiful theory has been developed. And this is almost a rigorous mathematical theory, and in this theory the role of Lie groups is replaced by the notion of loop groups. A loop group is the infinite dimensional group of mappings of a circle into an ordinary Lie group. So for every Lie group there is a loop group corresponding to it. The theory of these are very parallel, and they're very beautiful results. All this has been very well worked out by physicists over the last 20-30 years. Now, to get down to levels 3 and 4 is more serious. I focused on this block here. This one is a theory here which is very similar to the theory of Riemann surfaces in dimension 2, and it is a theory not of complex 2-dimensional surfaces you might think. It's a theory of real 4-dimensional manifolds which I want to call self-dual. In 4 dimensions, if you have a Riemannian metric, then you have a curvature tensor and it has many component parts. In particular, it has a part which is called the conformally invariant part of the Riemann curvature. It's called the Weil tensor. This Weil tensor breaks up into 2 parts, so-called self-dual and anti-self-dual. So if you have a conformal manifold in dimension 4, it may have one half of the Weil tensor vanishing and the other half not vanishing. Those are called self-dual. These manifolds, and the difference in self-dual and anti-self-dual is very much like the difference between holomorphic and anti-holomorphic on Riemann surfaces. And this theory is a theory which is very well suited, beautifully suited to Penrose's twistor theory. You can study this theory by going to a 3-dimensional complex manifold called the twistor space and using complex variable theory in 3 dimensions to get beautiful results about this 4-dimensional story. This theory is very deep. It includes things like work of Donaldson on 4-dimensional manifolds, but you can do many things parallel to what you can do here. So at the moment, this is something which is very much under investigation. I'm looking at it. The physicists are looking at it. There's a lot of work going on in this area. And so we've made a step from this to there. I have some ideas about this, which I won't explain. And then the last step would be to go down to the 4, where you should get down to things of dimension 8. See, this was dimension 1, 2, 4, 8. The dimensions go geometrically, not additively. Not 1, 2, 3, 4, but 1, 2, 4, 8. In 8 dimensions, there's a special geometry. If you have a Riemannian manifold of any dimension, then in general its curvature tensor has no special properties. But there are some kind of geometry where the curvature tensor has a special property. Those are called special holonomies. For example, these self-dual ones, if you have what are called self-dual Kähler manifolds, they're a special class where the holonomic group is SU2. You can have complex manifolds with holonomic SUN. You can have various groups, but there is special class in dimension 8 related to the octonions, which are called the manifold with spin several holonomy. It's the last of the exceptional list of holonomies. They're classified, and there exists one. There's one in dimension 7 related to exceptional group G2, and there's one in dimension 8 related to spin 7. This is all closely related to the geometry, to the algebra or the geometry of the octonions. And this manifold, this particular kind of geometry, these dimensions, is the one which one would naturally look at if one's following the proposal I made. The octonions should be studied in detailed geometrical form. And this should be the part where you begin to hit the hard part of Einstein's theory. So when you get down to here, this is the bottom row, you see, this is where it's supposed to be the exceptional groups. Here they are in the form of geometry. This is somewhere where we would expect Einstein's gravity to be really visible. And this geometry is theoretically known. A little bit of work has been done on it, but it's still very much unknown territory. A lot of work here to be done for the younger generation. If you're a young geometer and you want to know where the future lies, I would recommend you to look at some of the work here. It's a very beautiful subject, but very little has been done. Very little is known. Even in the 7-dimensional case, not much is known. So this is a new field of geometry which has remarkable properties. Some work's been done on it, and it looks very promising for the future. And my hunch is that this is a key part of understanding what we need to do quantum gravity. But that's my hunch. 50 years time, some of you old people are back. You'll say, I heard, Atiyah talk about that. And, he was right after all. Well, maybe you are right, maybe wrong. Who knows? We can't predict the future. But, if you have to make predictions about the future, they should be beautiful predictions. If you make an ugly prediction, nobody's going to like it. You make a beautiful prediction, it's right. They will say, here was an inspired poet. So, I like to make beautiful predictions because I believe that, if God created the universe, He did it in a beautiful way. Why would He make the universe based on basic equations? All this beautiful mathematics around. Surely God knew the mathematics first. He knew about the exceptional groups, and He wasn't going to use some stupid group, uninteresting group, when He could have a beautiful group instead. So God chose the beautiful things in mathematics because they were there, and He wanted to make a beautiful universe. Everybody has to believe that, whether you're an ordinary believing Christian or a Muslim or a mathematician. Believing that the universe is built on beautiful mathematics seems to be the best thing you can make. You should believe that. If you're wrong, well, it's unfortunate. God made a mistake somewhere in His Psalms. He didn't get it right. But as long as he did his homework right, He made a beautiful universe. And we may take a long time to get there. It may not be, in our lifetime. All we can do now is to point in the right direction. And I've been pointing in these directions because I've had some thoughts about these things. I see what the physicists do. The physicists are doing very clever things, but they tend to be going round and round in circles. They're not quite sure what the final picture is going to be. I can try to describe that in the following way. There are, well, maybe I'll come to that in a moment. I'll say a word about Alan Kohn. Alan Kohn, as I mentioned before, had a very beautiful theory of non-commutative algebra, non-commutative geometry rather. He takes algebras and he applies geometrical notions to them like space and curvature, bundle. And using this model, he has even produced his approach to the standard model of physics. And he takes a situation where the space-time is not just one copy of space-time, but two copies of space-time very closely, very little distance apart. And on this model, he builds his machinery, he gets something like the standard model, which is quite a remarkable achievement. And in arithmetic, he ends up with some approach to the Riemann hypothesis, which is where the number theory came in. I've mentioned here the famous relation between algebraic geometry over finite fields and the Riemann hypothesis over finite fields, which was conjectured by André Weil and proved by Deligne and Grothendieck many years ago. Now, in Kohn's theory, his non-commutative geometry is based on a homology theory, which he calls cyclic homology, and is developed for associative algebras. See, if you have ordinary geometry of functions in a space are commutative. And ordinary topology uses ordinary homology theory and so on. But if you're dealing with non-commutative geometry, your only thing you have associativity still, then the associative law has an important property, and for example, if you think about matrices, the important property of matrices is that if you take three matrices, A, B, and C, and you multiply them together and take the trace, that's the same thing as multiplying them in a cyclic order, CAB, and taking the trace. You usually see that. So cyclic homology is based on the notion of traces of triples of matrices, and it leads to his geometry. Now, Kahn's theory only deals with associative algebras, so he can't deal with the Arctonians. So that's why I think he's not quite finished. I mean, his theory is very beautiful, but it doesn't totally convince the physicists. The way he gets into geometry relativity is rather ad hoc. He gets a standard model, perhaps convincingly, but it doesn't get to the real heart of gravity. And I think the reason is that his theory deals with associative algebras only. And as Dirac thought associative algebras were the beautiful things, but both of them missed out the next one. So that's my view. Now, when I'm talking about Alan Kahn, let me make one other comment. Alan Kahn's theory is very algebraic. It's based on algebra and also based on the spectral properties of operators. And he links it to the physics where you look at the spectral lines of atoms and so on. Very much like Heisenberg did when he got into matrix mechanics. And I think the difference between my philosophy and Kahn's philosophy is like the difference between the philosophy of Heisenberg and the philosophy of Schrödinger and Dirac. Heisenberg developed algebra, commutation relations. Kahn is very much in the spirit of Heisenberg, whereas Schrödinger wrote down a differential equation, and Dirac wrote down an even better equation. And this equation later on was shown to be equivalent to Heisenberg's formulation, but from a different point of view. So I belong to the Schrödinger and Dirac school, and Kahn belongs to the Heisenberg school. We may be more or less equivalent for many purposes, but for the purposes of gravity, I think Heisenberg doesn't win. I mean, there's something missing here, as yet. That was a philosophical remark.